Hi, today we're going to do number 110, balanced binary tree. So we're given a binary tree and we want to return true and false if its height is balanced. And height here is when there's two subtrees. For every subtree, they don't have a difference of more than one. So we see here for this subtree, it has a difference of 1. But here we have a depth of more than 1, 2. So we return false here and we return true here. So how can we solve this problem? And since we're looking at the depth of the binary tree, it makes sense to use the DFS using recursion to see it, because if we can see if each subtree is a balanced or not, we can turn that up to, we can divide the problem to see if each subtree is balanced or not, and use that to figure out if the entire tree is balanced or not. So for the brute force way will be a top-down approach, where we're going to check each node. For each node, we want to calculate the subtrees of it. And with that, we can, with the height, check if node is balanced or not. And then we get it, then we recursively check all the children. And so for this, the time complexity is going to be O of n squared, where n is the number of nodes. Because for this one, we're going to check all possible. We have to, for this 3, we have to check the height, and then check the height on this side and compare it. And then for this 9, check out the height and compare it with the 20 on this side and check the height. So it's going to be O of n squared, and then space complexity is going to be O of h, where h is the height of this tree. So if it's balanced, it's going to be O of log n, and if it's unbalanced, it's just a straight line, it's going to be O of n. And now how can we improve this? We can use a bottom-up approach. So instead of going down and check, and we have to do this repeated work of calculating the height for each node. So we can just go all the way to the bottom and then get the left and right and get the height of each subtree. So we recursively get the height of left and right subtree, and then we check if current node is balanced. And then we want to return the height to the parent. We'll say the subtrees. So as we go up, we're going to go down, and as we go up, we're going to get the height, and with this height we can calculate if it's balanced or not. So this way it improves our time complexity by just being O of n, since we're just looping, recursively going through each one of them once. And then the space complexity is going to be the same O of h, where h is the height of the tree. And since this one has a better time complexity, we're going to go with the bottom-up approach, but I'll show you both ways. So for the bottom-up approach, we have this function GFS as we go through it. And in it, if it's a null value, it's going to be returned 0. Now we want to cap the left side, and then we want to do the right side. And here, what we want to do is that if it's unbalanced, we can leave this call stack, recursive stack, and return -1 to figure out if it's not balanced. And if we do this on the left side or right side, we can exit early. So if left equals -1, return -1. And same thing for this right side. If right equals -1, return -1. Now we check if the height's balanced now for the current iteration of it. So if, and then we're going to have to use absolute left minus right. If that's greater than 1, we know that it doesn't fit, so return -1. And then we just return back the height, and we do just 1 plus math.max, either the left or the right side. And here we'll have to call it. So return DFS passing the root. So return that. So if it's a -1, it's not balanced. So as long as it's not, so we can just return if it's not equal to -1. Or else we'll get the height. And if we get the height, it's true, so it's balanced. Great, so now we can do it with the brute force way. So here we're going to need a helper function to calculate the height. So function height, passing the node. So if it's negative, if it's null, so if node is not true, return 0. And then we do the left side. Left equals the height of the node dot left. Const right equals the height of the node dot right. And then we just return 1 plus the max left or right. And now we're going to call this as we do DFS. So function DFS. And it takes in a node. So if node is not there, it's balanced. And now we calculate the left height and the right height. Okay, and now we check if it's valid. So now we check if it's unbalanced first, because we have to recursively go through it. Math.apps left minus right. If it's greater than 1, we know that it's false. And now here we're going to return DFS of going through the left side, node.left, and DFS node.right. So it makes it all the way down. And now we have to call the GFS. Great. So these are two ways we can solve this problem, both using DFS. One is a brute force way, top-down way, where for each node we calculate the subtree of these children, and then see if it's a balance or not. The other way is we just keep going down until we get to the bottom, and then we get the height, and then once we have the height of the subtree, we compare it with we compare the left subtree and the right subtree, and with that you can check if it's balanced or not. And by doing it that way and going up the call stack, you can just do it in O of n instead of O of n squared. And that's all. Thank you.